Stop overpaying for expensive resin kits that don't even work. I'm going to show you how a simple $1 bar of soap can permanently erase deep windshield scratches using a forgotten industrial hack from 1955. This isn't just a temporary fix. We are leveraging optical science to restore total clarity today. There's a bar of soap that costs $1. It fills windshield scratches permanently, not by coating the surface, but by forcing high-density fatty acids into the glass pores through dry friction. Optical glaziers and industrial glass technicians used this method for decades before the automotive glass repair industry was built around selling you a resin kit. They did not stop using it because it failed. They stopped because a $1 bar of soap cannot generate the margin required to sustain a $400 professional resurfacing service. This is the story of the 1955 industrial hack. The windshield repair industry spent 70 years burying under a catalog of products that do not work as well. Welcome to Unearthed Lab. The problem begins with how light interacts with a scratched glass surface. An undamaged windshield allows light to pass through at a consistent refractive angle. The view is optically coherent. A scratched surface disrupts that coherence. At the microscopic level, a scratch is a valley with jagged walls. When light strikes those walls, it scatters in multiple directions simultaneously, a process called diffuse reflection. The result is the haze and glare that makes a scratched windshield dangerous in direct sunlight or oncoming headlights. The depth of the valley determines whether the scratch is addressable without resurfacing. Surface scratches that do not penetrate beyond the outer silica layer can be optically resolved by filling the valley with a material whose refractive index approximates glass. The light path is restored and the scatter eliminated. This is the foundational principle behind every windshield scratch repair product on the market. The active mechanism is called optical index matching, filling the scratch valley with a material transparent enough to redirect light along the original path, rather than scatter it. The automotive glass repair industry built a product category around this principle using UV-cured acrylic resins. These approximate the refractive index of glass while curing to a hard surface. A professional repair kit costs between $40 and $400. Traditional bar soap, saponified animal or vegetable fats, contains stearic acid, palmitic acid, and oleic acid at 30 to 60% by weight. These long-chain fatty acids are semi-transparent solids. Their refractive index runs between 1.43 and 1.46. The refractive index of standard automotive glass is 1.52. A fatty acid filling a scratch valley in glass of 1.52 does not achieve perfect optical matching, but it reduces the angular scatter of light at the scratch interface dramatically. The haze and glare are eliminated. The industrial origin dates to 1955. Optical technicians at American plate glass manufacturing facilities were documenting methods for restoring surface clarity to industrial glass between production runs. Internal bulletins from Libbey-Owens-Ford describe fatty acid application as a standard field method for scratch mitigation on production glass. Those bulletins were circulated to plant maintenance personnel, not to consumers. The Libbey-Owens-Ford bulletins from 1955 were not the only documentation. Pittsburgh Plate Glass Company maintained internal protocols describing fatty acid application for scratch mitigation on architectural and automotive glass. Those protocols were retained in plant engineering files through the 1970s. Neither company had a commercial incentive to translate those protocols into consumer products. Their business was manufacturing glass, not repairing it. The repair market that emerged in the 1980s was built by a separate industry with no connection to the industrial glass knowledge base. The Society of Glass Technology in the United Kingdom published a technical review in 1968 documenting fatty acid-based surface treatments for optical glass restoration. The review was distributed to optical manufacturing facilities in Europe and North America. It was not a consumer document and was never indexed in any retail or trade publication. The institutional knowledge was circulating inside the industry. It simply had no mechanism for reaching the consumer. The method was institutional knowledge inside the glass manufacturing sector, never translated into consumer-facing documentation. By the early 1960s, automotive glass installers in the United States were using the fatty acid fill method to assess surface scratches before replacement decisions. The technique appeared in regional trade publications for auto glass shops, not in any consumer publication. It was professional knowledge, retained inside the trade. The consumer automotive glass repair market emerged in the 1980s, initially targeting windshield chip repair. By the 1990s, scratch repair kits using UV-cured acrylic resin had proliferated across the automotive aftermarket. These kits carry a critical long-term failure mode the industry does not advertise. UV-cured acrylic resin yellows under prolonged UV exposure. A repair performed with a standard kit begins to discolor within 12 to 18 months. The yellowing increases light scatter within the repaired area, eventually producing a visual artifact worse than the original scratch. Fatty acids do not yellow under UV exposure. Stearic and palmitic acid are photochemically stable. They do not undergo the chain scission degradation that causes acrylic yellowing. A fatty acid fill is optically stable over years of sun exposure, in a way an acrylic fill is not. The windshield repair industry does not publicize this comparison. It does not conduct independent studies comparing fatty acid fill longevity to acrylic longevity. A method that costs $1 and lasts longer than a $40 kit is not a product category. It is the end of one. The U.S. automotive glass repair and replacement market generates over $4 billion annually. Windshield replacement averages between $250 and $500 per vehicle. A scratch repair that prevents replacement, performed with a $1 consumable, is a direct reduction in that revenue pool. The fatty acid method does not fit anywhere inside that economic model. So the 1955 technical bulletin stayed in the plant maintenance archive. The trade publication reference stopped being reprinted after the 1970s. The consumer learned about UV-cured resin kits instead. The physics of optical index matching does not differentiate between delivery mechanisms. If fatty acid in a scratch valley reduces light scatter by the same principle as an acrylic resin, controlled reduction of the refractive index discontinuity, the substrate does not change and the optics do not change. The $4 billion automotive glass market depends on a specific consumer behavior, the assumption that glass damage requires professional chemistry. That assumption was built deliberately through product placement, professional certification programs, and trade advertising that positioned resin kits as the only credible solution. The glass manufacturing sector never shared its internal methods with the consumer automotive market. When the automotive glass repair category emerged in the 1980s, it developed its own chemistry, acrylic resins, without reference to the fatty acid protocols documented in the industrial glass literature. The two bodies of knowledge developed in parallel. The institutional knowledge never crossed into the commercial one. The consumer market was never designed to find what the industrial sector already knew. Professional windshield repair certification programs teach UV-cured resin application as the standard method. The professional certification programs that dominate the windshield repair trade were established in the 1990s. The same decade acrylic kits became the standard consumer product. The National Windshield Repair Association, founded in 1994, published training materials based entirely on resin chemistry. No alternative fill methods were documented. A technician certified through the standard industry pathway in 1995, 2005, or 2015 received identical training on acrylic resin application. The fatty acid method was not in the curriculum, not because it had been evaluated and rejected, but because it had never entered the consumer repair ecosystem. The certification programs were built to serve that ecosystem. What it did not contain, they did not teach. Those programs are funded in part by the companies selling the resin equipment. A technician certified on acrylic resin has no professional reason to investigate fatty acid alternatives. There is no training material pointing there. The knowledge gap is self-reinforcing. The difference between a $1 bar and a $40 kit is not in the optical result. It is in who profits from your not knowing the result is comparable. Not every windshield scratch is addressable with a fatty acid fill. The method works on surface scratches, those that do not penetrate through the outer silica hardening layer. A scratch you can feel with a fingernail but cannot catch the edge of is a surface candidate. Run your fingernail perpendicular across the scratch. If the nail slides smoothly with only slight tactile sensation, the scratch depth is appropriate. If the nail catches a defined edge, the damage may exceed what index matching can resolve optically. The Society of Glass Technology in the United Kingdom published a technical review in 1968 documenting fatty acid-based surface treatments for optical glass restoration. The review was distributed to optical manufacturing facilities in Europe and North America. It was not a consumer document and was never indexed in any retail or trade publication. The institutional knowledge was circulating inside the industry. It simply had no mechanism for reaching the consumer. The preparation step determines whether the fatty acid bonds to glass or to contamination. Begin with a 90% isopropyl alcohol wipe on the scratch area. Road oil, silicone residue, and wiper blade deposits create a barrier the fatty acid cannot penetrate. Allow the glass to reach optimal temperature before applying. Glass contracts in cold conditions and the scratch valley narrows. In direct sunlight, surface temperature reaches 40 to 60 degrees Celsius. The silica structure expands and the scratch valley opens to maximum width. Use a heat gun at low setting for 30 seconds if sunlight is unavailable. The expansion is slight but measurable, and it determines whether the fatty acid can fully seat into the base of the scratch valley. Do not use water at any stage. Water dissolves the fatty acid matrix as it is being applied, reducing structural density before it can seat into the glass. The technique depends entirely on dry friction. Liquid contact at any point disrupts the bond. Take a bar of traditional tallow-based or coconut oil-based soap with a firm, waxy texture. Avoid translucent bars. Translucency indicates glycerin dominance rather than fatty acid dominance. Basic white dollar store bars are consistently appropriate. Apply the bar to the scratch with heavy, sustained pressure and a linear motion along the scratch direction. The objective is to force fatty acid into the valley through friction, not to spread it across the surface. Pressure must be sufficient to generate mild heat at the contact point. The diagnostic signal is color change. A dry, unaddressed scratch appears white or silver against the glass. That is the diffuse reflection from the jagged walls. As fatty acid fills the valley, the white color diminishes. Continue until the scratch no longer appears white under direct light. Do not apply water between passes. If the scratch remains partially visible, apply more pressure and more dwell time under friction. The fatty acid must be forced into the glass mechanically. It will not flow into the scratch without the combination of pressure and frictional heat. After filling, a white residue remains on the glass surface surrounding the treated area. This is excess fatty acid that did not enter the scratch valley. Remove it with a dry microfiber cloth using circular buffing motion and moderate pressure. The buffing generates additional heat that helps seat the material already in the scratch and polishes the excess from the surrounding glass. Do not use a wet cloth. Water contact at this stage will dissolve the surface of the fill before it has fully seated. The fatty acid mechanism has a secondary benefit. Acrylic resins do not replicate. When driven into the scratch valley under dry friction, the material distributes along the full depth profile, including microfractures branching from the main valley that are invisible but contribute to light scatter. Acrylic resin applied by dropper fills the main valley but does not penetrate secondary microfractures without pressure. The pressure-driven fatty acid fill reaches where a dropper cannot. The result is a more complete optical restoration for scratches, with complex fracture profiles. The diffuse scatter from secondary microfractures, contributing to haze under low-angle light, is addressed by the pressure-driven fill in a way a drop-applied resin cannot reach. Test the result under direct artificial light, a flashlight held at a low angle to the glass surface. This is the most demanding optical test for scratch visibility. If the scratch is no longer detectable under direct angular light, the fill is complete. If residual haze remains in any segment, repeat the application on that area with additional pressure. The total time from preparation to finished result is under 15 minutes for a standard surface scratch. The durability comparison favors fatty acid over the long term. UV-cured acrylic begins to yellow within 12 to 18 months under direct sun. The yellowing is photochemical degradation of the acrylic polymer chains. It cannot be reversed without removing the fill and reapplying. Fatty acids do not undergo this degradation. Stearic and palmitic acid are photochemically stable at the intensities encountered in automotive glass. A fatty acid fill does not yellow, does not cloud, and does not degrade optically over years of sun exposure. I need to be honest with you about something. The fatty acid method has a durability limitation. Car wash pressure washing partially displaces the fill over multiple cycles. The fill is stable under rain and normal wiper operation, but sustained pressure degrades it faster than cured acrylic. If the vehicle is pressure washed regularly, plan for a touch-up every 3 to 6 months. Reapplication takes under 2 minutes and costs nothing beyond the original bar. This is maintenance, not failure. The fill material is still present. The touch-up simply reinforces what pressure wash partially displaced. There's also a transparency limitation. Under extreme oblique lighting at specific angles, a filled scratch may remain faintly detectable. A professional acrylic repair at comparable depth achieves marginally better optical match under those extreme conditions. The long-term cost comparison is where the suppression becomes most visible. A professional acrylic repair yellowing within 18 months requires a second repair at the same cost. A fatty acid fill stable for years at $1 is a different economic relationship entirely. Over 5 years, 2 professionally repaired scratches requiring 1 replacement repair each due to yellowing cost between $80 and $160. The same 2 scratches addressed with fatty acid and maintained with annual touch-ups. $2 total. The windshield replacement decision is where the stakes are clearest. A surface scratch not addressed grows in severity as road debris and wiper friction widen it over time. Filling it on first appearance prevents a replacement costing between $250 and $500. The monthly inspection protocol takes under a minute. Under direct sunlight or flashlight at low angle, scan the windshield for areas where fill has lightened or scatter has returned. These indicate partial displacement by water or wiper friction. A 30-second reapplication restores the fill completely. The bar itself lasts for dozens of applications. A single dollar store bar addresses one vehicle's scratch maintenance needs for 2 to 3 years. The economics, over a 5 to 7 year ownership period, are not comparable to any resin-based alternative. They are in a different category entirely. The $1 bar is not competing with the $40 kit. It is competing with the $500 replacement. The core argument holds. A $1 bar addresses the same optical problem as a $40 kit through the same physical principle. Optical index matching at the scratch interface. The fill lasts longer under UV exposure, costs 100 times less, and requires no curing equipment. You cannot patent a fatty acid. You cannot trademark the refractive index of stearic acid. The optical physics do not care about the packaging on the product applying them. If you have made it this far, you already know more about windshield scratch repair than 99% of auto glass technicians and repair kit manufacturers combined. Subscribe and share this with someone who's about to spend $40 on a kit that will yellow before next summer.